Hello everyone, welcome to the webinar on PSCAD custom model development. I'm Rohit Jayasinghe and I'm responsible for mainly the EMTDC engine and the model development models in PSCAD. With me I have Darshana Muthamani, our simulation expert. The content of today's webinar, we will try to cover the items listed here. The program structure of EMTDC and how electrical circuit components and the control components, control circuits are treated. The numerical solution to differential equation and how the data is stored, how data is stored and the memory is managed. Then we will go with an control system or mathematical block example, and then how we can model simple electrical circuits, and then with examples of electrical components, electrical elements. So it is, before we go into custom model development, it is necessary to talk up a little bit background information so that it's easy to understand what is happening in each piece of a component that we develop. What is in this slide is the simplified program structure just relevant to this presentation. The four shaded boxes, DS9 begin, DS out begin, DS9 and DS out, they basically represent four functions or subroutines in the program. The content of these subroutines are filled based on the what components you put in the drawing canvas and how you connect it. So if you look at this slide, DS9 begin and DS out begin, they are executed only once. So that means these are the ideal place for if you want to do a one-time computation and then use that later in the every time step. DS9 is called before the network solution. So if you have something piece of component that is going to affect the solution in the current time step, we should have it in the ds dyne, and ds out is after the solution. So this is the place like you can measure the output, which would have the latest information for that time step. And after that, the time step is incremented, and then we are going back to ds dyne. The begin sections are the ds dyne begin, and ds out begin is the ideal place to convert the user supplied data to the required form asked by the model, the code executed in ds dyne or ds out. This is an example of a simple integrator. To solve the differential equation of we use the trapezoidal rule. So when you use the trapezoidal rule, here the integral value of time t is the integrate output at t minus delta t plus the average of the input value at this time step and the one time step ago is multiplied by the time step. The next I'm going to talk a little bit about the different storage arrays that we use within components. First, we have store arrays. This is like if you want to transfer data from one time step to the next time step. So for example, in the previous integrator, the integrator value at last time step, we need it in this time step. So in that case, we would use the store array. And then we have with PSCAD X4, we have this new array that came in, the RTC array, runtime configuration storage arrays. The purpose of this array is to transfer data from begin section to the ds dyne or ds out. So anything that is computed once right at the beginning based on user supplied data, we convert them into the required form, and then we pass it to ds dyne or ds out. Using RTC arrays. The last array, it's it's really new, but actually we needed this array to in the creating black boxes, so that was the reason this new array came up. There's hardly any components that's using this array, but the idea here is to transfer data from DS9 to DS out or DS out to DS9. If you transfer it from DS9 to DS out, there is no time step delay. But if you are coming from DS out to DS9, then because the way the structure works, there will be a one-time step delay when the data is accessed in DS9. I put the array names as marking with an X. The X could be L, I, F, or C, and that L, I, F, and C corresponds to different types of arrays, logical, integer, floating point, or complex. To show this graphically, so this is the RTC array showed in blue. The purpose is going from begin sections to DS9 or DS out. Storage array in yellow, it's from time step to time step, and STX FR array is to transfer between DS9 and DS out. So now we have a little bit of information. So now what I'm going to do is start working on a simple component, creating an integrator. So let me switch my screen to my other screen where I have the PSCAD loaded. This is PSCAD 4.6. So I'm going to create a new case. And call it integrator. So the easiest way to start the component is use the component wizard. So start the component wizard, and we have to give a name. And we have one input, one output. I'm going to add the ports, connections. I'm going to call my input as X on the left side, or output as Y on the right side. I'm going to change this to an output. Right now I'm working on scalars, so I keep in the dimension as 1. Finish. So it creates the skeleton of a component. Now it is for me to fill this component with the math needed for the integrator action. So I'm going to edit the definition. Into the script. By default, you'd have a Fortran branch computation, so I'm going to use the Fortran section now. The green highlighted column is the column 6. Don't start anything from column 6 because that's Fortran has a special meaning for column 6. So I'm going to start from column 7. First, I need my old X value from storage. Each storage array has a pointer, and every time is the name of the storage array prepended with n for the pointer. And my output which is x and y, I had to put the dollar sign to refer a parameter or a port. Instead of dividing by 2, I'm multiplying by 0.5 because the multiplication is more efficient than dividing a number. And now I have the integrate output. Now I have to save this for the use in the next time step. Both input and the output. This is basically it, but now because we have used 2 storage locations, we have to increment our storage pointer by 2. So now we basically have a simple integrator component. One thing I missed here, the 2 signals I created, X old and Y old, I have to define them as real signals, floating point signals. And the one other thing I'm going to do is I have to inform PSCAD how much storage I'm using in this component. So if we need more storage, when it dynamically allocates the storage right at the beginning, it knows how much storage to allocate. Just because this is off center, I'm just going to move this to the center of the component. So now we have a simple integrator. So let's create a signal. And see, make an integrator. I'm creating a sine wave. Cosine. I have 60 hertz. So I'm going to connect this output of this. X. It is not necessary that you give a name to the signals, but it makes it easier to follow. I'm going to plot my input. Just going to say to use the signal name as title. Y.
No signal name there.
Why didn't create it?
You come with RT1.
Let's just let's run this. Maybe I should have created in two different. I'm going to insert another graph. So this is what we got. Because we didn't define the initial value of the integrator, we have an offset. So it started from 0. So I'm going to modify this component to give an initial value. New parameter, real. By 0. Initial value of integrator. I'm going to keep this as literal right now. Default value is 0. And then I'm going to add the code here. If I am 0, my the previous y value is the what we defined. So I'm going to give about 0.0025 minus so that it is balanced around the. This is not an exact value, I'm just guessing. Okay, now we have an initial value, it's roughly centered around the y equals 0 axis. Okay, here in the component, in the parameters, there are three types: literal, constant, and variable. I'm going to talk a little bit about these three types. Let me switch my screen again to the other monitor. So this is the meaning of those three types of parameters. Literal means it has to be a number. Constant, it's not something that varies. It is constant for the entire run. But you can assign that value to your signal name and use that signal name. So this is ideal if you want to pass values from the begin routines to the DS in or DS out. And then variables means that signal could change at any time during the run. So if you think it how this literal is a subset of a constant, and constant is a subset of a variable. That means a signal which is asking for a constant, you can enter a literal value. It doesn't have to be a signal name. And where you need a variable type input, any of this would work. There's another way of presenting literal, constant, and variable. Literal and constant, you can, because they don't change, you can use it for one-time computations before execution. Constants and variables, you can have named signals. Literal, because we know what the value is before we generate the Fortran files from the circuit components, we can use it to pre-process the code and have a simplified code if you are using literal parameters. But then you may be wondering why we want to use constant or literal. The constant helps if you want to pass a signal from a page module to a component inside. I'm going to change my screen again to PSCAD, and loading up an example Scott connection. So this is actually a page module, and I have parameters in this page module, frequency, which I'm using as the frequency of the transform model used inside. So this helps to transfer constant signals from page module to a component inside. So if I want another Scott transformer, I can simply copy paste this and change that to, so instead of 60 Hertz, I can have 50 Hertz Scott transformer. But both are the same, but uses two different signals to pass to the components inside. Next, I'm going to back to the integrator, and then we have a lot of segments and components. I'm going to explain a little bit of these segments, what they are. So let me switch my monitor again to PowerPoint. The segment branch is used to model electrical branches, where the branch is connected from which node to which node, that information and type of branch, and checks that we can generate based on the literal or choice input parameters. We can generate warnings or errors depending on what the user enters. It comments, it's self-explanatory. Then we have computation segment. We can use literal or choice parameters to create new signals. And this is where I said like we can do some pre-processing to simplify the code generated if you have some literal parameters. And there are three segments, DS9, DS out, Fortran. All three are used for the related Fortran code. So this is the part that is used in building the DS9, DS out, or DS9 begin, DS out begin. So if you write it in DS9, it goes directly to DS9. Same way, if you write it in DS out section, it goes to DS out. If you write it in Fortran, then depending on where this component is placed and where the input is connected, PSCAD decides whether to put it in the DS9 or DS out. So this is helpful in something like, for example, if you have a gain block, you may use it in you may develop a exciter model which is the gain block, so which you need it in the DS9 because you need to have the exciter at the current state for this time step, or else you may have used the same gain block to multiply the measured current and plot it in with a different scale. So then in that case you want the that code to be in the DS out before the plotting. So if you write it in Fortran, then the PSCAD decides what's the best place to put the code. So generally, if you're writing the electrical components, you're writing into DS9 and sometimes a little bit of code into DS out and mostly DS9. But if you're writing a control component, it's it would be generally in Fortran segment. And the few more segments, the flyby, that is, you can use it to give a flyby help on what the ports are. You can give a description on, like, when you move your mouse pointer over the port, it gives a flyby help what the port is. Then you can link a HTML help file or another help file in the help segment. Matrix file is used on how the conductance matrix is filled by this routine, because sometimes you may have a component that has many nodes, but it may not be filling all the elements in that matrix. So it is helpful when ordering the nodes so that we can use the most sparse conductance matrix. And if the model needs some additional information, that you can write it in the model data section without passing them in the as arguments to a subroutine. And there's a segment called transformers that basically has the information if transform is used in this component, the developed, how the windings are connected and how many windings are there in that transform model. So now let's look at how a simple electrical branch can be modeled. For this example, I am using an inductor. So the inductor equation is the voltage is inductance times the derivative of current. And if you use the trapezoidal rule, we can write it in this form. The average voltage is L, and the difference of current divided by delta T. And if we reorganize it, we can write it in this form. This is basically like if we can convert, or we can think of it as in this form, resistance and a voltage source. So next I'm going to show how we can do this. just give me a second here. The, I'm switching the monitors. This is the details are I'm going to get use the method. This is in the help and EMTDC interface into electrical network. So I'm going to use the variable RLC routine, which has a interface to a variable resistor and a variable voltage source. So there is a new case. Again, create a new component. My inductor 1, 2 ports, and they are electrical ports. So I'm going to use the variable RLC branch before going into script. We need a parameter. So new parameter, I'm going to call it L. Inductance. Unit is Henry. So back to script. The code written between begin and end begin goes to the okay, I excuse me, I don't want to use the Fortran segment, I want to use the DS9, and Fortran I don't need it. On the branch. Subsystem number $SS, that's not, and this is the branch number, and I'm defining it as a resistive branch at 0. This is explained in the help because of the time consideration, and skipping that part, but you can see it after the webinar. I need 2 real signals. I use a personally I use a naming convention like this for all the temporary signals that I create in a component. So the first variable is the resistance created by the inductance in our representation, which is, if you remember the previous slide, 2L over delta T. And the second signal is the value of the voltage source. There's the branch current times my resistance plus the voltage across the branch. The B branch is a function, so because of that I'm going to declare that the CBR is an array available to the user. So if I this is the, if you want to model the inductor as a variable resistor and a voltage source, that's one way, and there's another way you can have it, model it as a current source in parallel with a resistor. I'll go to that one too after this. And we use BR for the branch number, which we haven't named it yet. So the BR is the between nodes A and B, and the breaker syntax tells it is a component the characteristics of that branch is switching or it's defined later. So now I have a simple inductor component, and let's put 0.1 henries. And let's add the source model, single phase source. I'm just going to make it ideal. Ammeter. And first, just to make sure whether we are getting the right result, so I'm going to put another real inductor connect it here, and then I'm going to call this IP, or maybe I2. Call this I1. I1. Copy paste. Same thing, and I want to plot I2. Create a signal, plot, and plot I2 too. Let's run this case. Hopefully no errors. Okay. And the both signals, both the inductor and the
My inductor.
they gives the same current for this voltage. So now let's look at creating this as a current source. This is the variable resistor, and then there's an example here. We can use the current source 2 routine to calculate the current injection and the conductance. Back to the my PowerPoint. So again, I can rearrange my inductor equation in this form. My current is conductance times the voltage across the branch and this current injection. Back to PSCAD. So now I already have this existing component. Instead of going through the component wizard, I'm just going to create a copy of this, my inductor 2, create instance. By 3. We are editing my Inductor 2 component. Instead of using the voltage source in series with a resistor, I'm going to call the current source my conductance is the inverse of this. It's 0.5 delta T divided by R, and the now to get the current source in parallel, I have to multiply the voltage by the conductance, and also we need the previous current through the branch. Need to change the order of arguments, subsystem number, branch number, conductance, and the current injection. So this component is modeled as a current source in parallel with a resistor, and this is modeled as a voltage source in series with a resistor. Oh, I did not do something right. Oh. Oh, this order is different. And all three are the regular inductor, resistance with series with voltage source, or a current source in parallel with a resistor. All three are giving the same output current. So if the component is simple, you can the mathematics you need to do is simple. You can write it here, but sometimes they are not. Then what you can do is write a Fortran routine and use that. For that, I'm showing an example. I'm not going to write a Fortran routing right now. If you look at the electrical interface, custom electric components, this example has modeling as a single branch, model a series combination of a resistor and inductor. The numerical method used is explained in this sticky note to the right, and different models uses different techniques, and here's an explanation. And if you this is the you can write a subroutine like this, and you can have multiple subroutines in one single Fortran file, and then call that subroutine in the component rather than writing the detailed math in the component script. I think we are a little bit above our time. So I'm going to finish the presentation here. If you have questions, you can type in or send an email to support@pscad.com. We are more than happy to answer any questions you have on creating custom components. Thank you for attending the webinar.
See you at the next webinar, which is, I think, on insulation coordination.
Yeah.
It's an application-based webinar.
That's end of April somewhere. Yeah, April 21st or somewhere. Next webinar. Okay. Thank you again.
See you next time.
See you next time.